In the first part of Chapter 9, we focused on bending stresses. Beams also have internal shear stresses, so that's what we will learn about now. If you take a deck of playing cards or index cards and bend it in your hands, you will notice that the cards slide against each other. That's a response to a shear load. If the cards were glued together and were not able to slide, then a shear stress would develop. We want to know the shear stress at a particular location within a beam's cross-section. In this diagram, the location where we are calculating shear stress is marked as a purple line above the neutral axis of the beam. There's a derivation in the book that you can read. The result is the general shear formula, tau equals VQ over IT. V is the applied shear load, which you can get from the shear diagram. Usually, we're interested in the maximum shear load, absolute value, so the biggest number regardless of whether it's positive or negative. Q is the product of y bar and A prime, where y bar is the distance from the neutral axis of the cross-section to the centroid of area A prime. A prime is the area between the location where we are calculating shear stress and the top surface of the beam. I is the moment of inertia of the entire cross-section, not just A prime. Lowercase t is the thickness of the beam at the location where we are calculating shear stress. Let's look at a beam with a rectangular cross-section. It's a 2-inch by 8-inch aluminum bar, and let's say the maximum shear load on the shear diagram is 30 kips. We want to know the shear stress at the neutral axis. Start by drawing the cross-section, marking A prime, the centroid of A prime, and the distance y bar from the place where we're calculating shear stress to the centroid of A prime. Y bar is 2 inches and A prime is 8 square inches, so Q is 16 inches cubed. The moment of inertia of the entire cross-section is 85.3 inches to the fourth, and the thickness of the beam is 2 inches. Putting it all together, the shear stress at the neutral axis is 2.81 kSI. We can compare this number with the allowable shear stress of the aluminum alloy. As long as the applied shear stress is below the allowable shear stress, the beam is safe in shear. Let's take the same beam, but calculate the shear stress somewhere else. If we pick a location 1 inch below the top of the beam, then the distance from the neutral axis to the centroid of A prime is 3.5 inches. Y bar is bigger than before, but A prime is much smaller, so Q is also smaller. The value of I doesn't change because it's for the entire cross-section of the beam. The value of T doesn't change because the thickness of this beam is 2 inches all the way from the top to the bottom. We end up with a smaller shear stress. What's the shear stress at the very top of the beam? 0, because A prime becomes 0 at the very top. The maximum horizontal shear stress in any beam is at the neutral axis, and it's 0 at the top and bottom surfaces. This is the opposite of what we saw with bending stress, where it was maximum at the top and bottom surfaces and 0 at the neutral axis. Here's another example, a 1-inch diameter round steel rod with a shear load of 500 pounds. It's tempting to calculate the numbers for y bar, a prime, I, and t, then plug them into the general shear formula. But in this case, it's easier to solve it algebraically first, because a bunch of the terms drop out. Instead of punching in 11 numbers into your calculator, there are only 5, and 3 of them are constants. This means you're less likely to make a calculator error as you solve the problem. It also means that if you have to repeat the calculations for a different diameter and shear load, you can plug a simple formula into an Excel spreadsheet instead of a series of equations, again, reducing the chances of error. The general shear formula is really useful for simple shapes, but it's a mess for complicated shapes because of the need to find y bar. Wide flange beams have complicated cross sections. We draw them as if they're made of perfect rectangles stacked together, but they are hot-rolled steel shapes with internal and external radii. It's easy to find a prime because it's just half the cross-sectional area A. However, finding y bar is tricky. You would have to find the centroid of the T-shaped A prime area, and that would be time-consuming. Instead, we have a shortcut method that's close enough to be useful and safe. The average web shear approach says that the shear stress equals the applied shear load divided by the depth of the beam and the thickness of the web. For example, if a 42 kip load is applied to a W12 by 14 wide flange beam, the resulting maximum shear stress at the neutral axis would be 17.6 ksi. For low-carbon steel, the yield strength in shear is about 40% of the yield strength in tension. So if this is an A992 beam, then the allowable shear stress is 40% of 50 ksi, which is 20 ksi. Since the beam has a shear stress less than 20 ksi, it is safe in shear.